this chapter. So we now come to the last topic, which is power. And power is defined as the rate of doing work, or you can say the rate of energy consumption. So if you're spending energy at a certain rate, that would be power. Now when we talk of rate, it means how much energy is consumed per minute or per second or per hour or per unit time, or how much work is done per unit time. So it's work over time, or energy over time. So you do so much total work in so much total time. This ratio becomes the average power during this time. Now, this would be the average power. So if you want the instantaneous power, that would be in the limit when the T or delta T tends to 0 of the work over delta T. That would become dW over dt, or dE by dt. Now, if we consider simply work as a force times distance, it's going to be a force F dot displacement, or let's write the displacement as an R, could be three-dimensional, over dt. That would be the power. Now this can be written as the chain rule applies to the dot product, and it becomes F dot dr over dt plus df over dt dot r. Now for the simpler case of constant force, if the force means constant, so this becomes 0, then the power is F dr over dt, which becomes F dot the velocity. So the force times the velocity become the power if the velocity is constant. Now as an example, we take the case of a lift, an elevator. So we have an elevator in which we have a few people, and there's a cable that goes up to the roof where there's a pulley of some sort, and there will be an electric motor, some kind of electric motor. Well, it could be attached right here, but let's say we have an electric motor. So this electric motor would pull this inwards, which would pull this upwards, and that's going to pull the entire elevator upwards. So as an example, if the mass of the elevator plus the people is m, and the motor is pulling it up at a constant velocity v, which is not changing, so the speed is v, then how much power does the motor have to spend or apply or consume? The electrical energy, how much electrical energy does it consume to pull it up at a constant speed? So the power is it's F dot V. So how much force does it have to apply? And here we see the tension upwards and mg downwards at a constant velocity. Sum of force in the y direction becomes 0 if it's may, but if ay is 0, being constant velocity, then it's going to be t minus mg is 0, and therefore t is mg, and the t is the force. So this is going to be tension times the velocity. Both are in the same direction, so it's simply their cosine theta is 1 because same direction, and that becomes mg times v. That becomes the power that the motor has to apply to pull this up at a constant rate. And you can calculate that to see how much power the electric motors would need for some lifts going at some speed, but you need the velocity. Now, if there is friction on the sides, so as it's going up, there is friction, then we would need to add that friction in it. That would be added over here. The tension with friction, then the sum of forces in the y direction is 0 if it's still going at a constant velocity. It's going to be T upwards minus friction downwards is mg, and therefore T is mg plus the friction, and you just replace this in here and you'll get the new answer with friction. And suppose you say that, well, the lift started from a floor and now it's accelerating, because it has to accelerate once it starts from rest, and to gain some speed it has to accelerate. In that case, with acceleration, then the sum of forces in the y direction is ma in the y direction, because now it's speeding up. And with tension, well, let's include friction, so tension upwards, friction downwards equals, and there's one more force downwards, minus mg, that's also the downward force, equals may. And so the tension is going to be mg plus f plus may, and that's the acceleration of the elevator as it goes up. And now plug this T in here and you'll get the power. Is this whole thing mg plus ma plus f times the velocity at that instant of time. So whatever is the velocity at that point in time, that's what it should. Now the unit of power will be the unit of work divided by the unit of time, or energy over time. So energy is joule and time is seconds, so it's joules per second, which we write as a watt, written as a capital W. So work is capital W and watt is also capital W. So we just have to note the context to determine whether it's work or the unit of power. So this is a watt, and in like electric consumption in our homes, normally we use a kilowatt, which is 1000 watts. And then by rearranging this equation, we say power is work over time, and therefore work is power into time. So if the power is a watt and time is a second, then work becomes a watt second, which is a joule. Now a joule is a pretty small unit, and a watt is also a small unit. So in homes, instead of watt, we use kilowatt. So it becomes, if we had a second here, it would become 1000 joules. But instead of using second, we use an hour. So this becomes what we call a kilowatt hour, written like this. And this means 1000 watts times 3600 seconds. That's 3.6 into 10 to the power 6 watt seconds, and a watt second is a joule. Right? Watt is a joule per second, so a joule is watt second. Let's bring it here. That becomes so many joules. So 3.6 10 to the power 6, so 3.6 million joules is 1 kilowatt hour of energy or work. And in terms of the electric bill, this quantity 1 kilowatt hour is called 1 unit of electricity, and that is what they charge us for. It charges between 10 to 12 cents for 1 unit per unit, or we can say 10 to 12 cents per kilowatt hour. The electric meter that we have is also designed so it measures kilowatt hours, how many kilowatt hours we have consumed. It does not find the power that we're using, but it integrates that power to get power times time, and it gives us how much is the work or the energy that we have consumed. So our electric meters are energy meters, not power meters. They don't measure the power, but they measure the energy that has been consumed, and that is what they bill us for, not for the power. Power is the rate at which you're using energy. So you may use a low power, small consumption per unit time for a long period of time, and you will be having much more energy usage. Or you may use a lot of power for a short time. So that what they're interested in is how much energy you have consumed. So it's kilowatt hours, and that's 1 unit of electricity. So if you have for example, one lamp of 100 watts, and you operate for let's say 10 hours, so how much energy you've used is going to be 100 watts divided by 1,000, so that it becomes whatever kilowatts, and multiply with the time, so it's energy times time, so it's 10, and it's already hours. So this is going to be 0.1 times 1. It's going to be with a 10, that's a 10, so it becomes 1.0 kilowatt hour. Now, as a sort of a slightly different example, if you have one lamp, 100 watts, and you operate it for 10 hours a day, and you have for example, a microwave that's 700 watts. You operate it for 15 minutes during the entire day, and you have an air conditioning system with 3000 watts. It turns on and off, so it's used for a total of, let's say, 5 hours during the day. And let's suppose you didn't have one lamp, but you have 5 lamps, each operating for 10 hours. So what is your total energy consumption per day? This is going to be 5 times 100 times 10, so it's energy into time in hours, divided by 1,000, and this is going to be 700 divided by 1,000 times 15/60 to make it hours, and this will be 3,000 over 1,000, so it's 3 kilowatt times 5 hours. So 3 times 5 is 15 kilowatt hour, and well, these can be calculated and added up, and you'll get some kilowatt hour per day as your usage. Okay, so you can solve this.